So welcome to linear algebra, specifically applied linear algebra for engineers. In today's class, we are going to start chapter 3. So this chapter 3 is something called as sparsity and compress sensing. Now, please understand this chapter is very important from practical applications. So when we look at the natural data sets like image data or speech data or communications, signals data. So this data has lot of sparsity. What that means is there are a lot of zeros, or there are some parts of that data set which are very close to zero. So for practical purposes, we can represent this data in a very compact notation. So for an example, uh, if you think about the popularity of the QR codes, QR code. So QR code is like a rectangular box and it has the binary images. So if you look at this grid, some grid is dark and some grid is white. And there is this particular pattern that is formed by these black and white pixels. Now, for the sake of discussion, let's consider I'm looking at the QR grid, which is by 20 by 20 pixels. So 20 by 20 pixels. Then if you look at the potential possibility of how many numbers I can represent. So the number that we can represent with this a very small data set is huge. So if you look at this is 20 by 20, so this will be 2 to the power of 20 by 20, which is 2 to the power of 400. You have these many numbers that you can represent using uh, distinct possible images. So you have these many representations in just a simple 20 by 20 QR code. Now, just to think about how big this number is, this number is larger than number of nucleons in the entire universe. So in entire universe. So what that means is a very simple image can represent a very vast data set. So if you look at something called as the natural image space, and this natural image space is typically a matrix, and this matrix is going to be very, very huge. So if you look at this natural image space, all the physical images that we see or that we can potentially represent either by pictures or drawings or sketches or anything that you can think of forms a very small subset of this huge image space. So what that means is whatever data that we have that is representing the actual image, as soon as we have a suitable basis, that means a proper coordinate system, we can represent this data set in an extremely teeny tiny uh, memory allocation, or basically the amount of real data, or if you think about the real meat and potatoes that form the data, is extremely small compared to the space that we have available. And you would notice that everything else is insignificant, and that is actually comparable to zero. So what that means is we can use this sparsity. Sparsity means closeness to zero. Sparsity in this image data set to represent lot of representations in a very compact form. So what that means is, if you think about a data set that is represented as in a matrix form or in a tensor form. So for an example, you could have a data set that is given as a matrix. So basically a matrix of numbers, or it could be a tensor, which means you have matrices stacked in on top of each other. So you have these matrices. So these can be compressed. So there are, in the last class, we talked about representing the images using a Fourier coefficient, using a wavelet basis. We looked at how do we compress an image using wavelet basis, a Fourier basis. But this is what we did in last lesson. And what we are going to do in this lesson is a little bit different. So here is what we did. So we have this image, or we have this data set. We performed either wavelet analysis, or we performed the Fourier analysis. And then what we did is we found out an important mode, or very small important coefficients in this data set. So basically, we found out the coefficients. If you have an image, then you are going to have a Fourier series coefficients around x and y. So you get some image space, and these are the Fourier coefficients that are spread. And what we did, we grabbed these Fourier coefficients and then transmitted or stored. So basically this information is transmitted or stored. And when we had to reconstruct, what we did, the basis was known. So we know the basis here. We know the basis here. And what we did, we just transmitted the Fourier coefficients, and then we reconstructed this whole image. So what that means is, if you look at the actual communication, or if you look at the actual image processing, there will be an IC, integrated circuit, and its sole purpose of that integrated circuit would be to take this data set, compute the Fourier coefficient, and then pass this Fourier coefficient into the digital form. And this transmission is received by another chipset at the receiver end, and this chip is also called ASIC, application specific integrated circuit, ASIC. ASIC that will receive these coefficients and then basically reconstruct the image. Now what that means is the basis is not transferred. the basis is already pre-programmed in this ASIC. So basis, or that algorithm to find FFT and to find IFFT, is already stored in this ASIC, and only thing that get transmitted are nothing but the coefficients in a digital form. That makes this transmission extremely efficient, and essentially you are just passing out the required or the most important data from point A to point B, and that is the basis for compression. You can do the exact same thing with a wavelet transformation. You can do something similar with any other orthonormal basis. But when you are trying to think about extending this, we have to ask ourselves is, if my initial data set, if this my data set, if this data set is sparse, do I really need a basis to transmit it? So, and the answer to that question is, here is an alternative way this can be done. So imagine you have this data set. Imagine you have this data set. And what I'm going to do is, in the first case, I actually scanned this whole data set. So I went line by line. As you can see, I scanned in the form of a raster, and then actually scanned this whole image and then computed the Fourier coefficients, passed those Fourier coefficients. But now what I'm going to do is, rather than doing this rastering, what I would do is I would do random capture of data. So basically, I would continue to capture data in a some type of a random fashion. And what I would do is I would use this random sample data. I would use this randomly sampled data, and I would pass it through this same process. So I would pass this through this same process. And it happens to be like, as long as if you meet certain conditions, and today we will look at those conditions. If we look at certain conditions, you are able to reconstruct this whole image based on this randomly sampled data, based on this image, which is randomly sampled data. Now, this is very powerful, and the classic application of this technique is in infant MRI. So as you know, if you want to get an MRI done, basically there is this dome and there is this platform. The patient is on this platform, the platform goes inside, patient has to stay still, and then basically this magnetron rotates and the imaging is captured. For adults, staying still is not a problem, but for infants, it's not easy. Infants don't stay still. So the scientists and engineers and physicians face this problem, like how do we do the MRIs for infants? So what was found out, that even though the infant is moving, if we use this approach, which is called as compress sensing, if you use this approach, which is called compress sensing, you would be able to capture the MRI accurately. What that means is, by interpolation, if the MRI was taking 10 minutes to complete, the whole body scan initially was taking 10 minutes to complete, then the whole body scan can now be completed in seconds. So that is the advantage of compress sensing. So all modern MRI machines, they use compress sensing. Even the uh, ultrasound machines, they use compress sensing. And all this is possible because the data that we are getting has lot of sparsity, which means that the data has a lot of junk that can be thrown away, and we can actually focus on the essential part of the data. Now, before we go to the aspects of compressed sensing and understand the theory behind compressed sensing, what I want to show you is I want to show you a simple example is how we actually look at the sparsity of image space. So what I'm going to do is I'm going to show you the MATLAB script, and this code again is given in the textbook. So let me share my screen. So if you look at this code, now this is a simple example wherein what we are doing is we are actually capturing an image of the jellyfish. And this jellyfish image is basically, as you can see on the screen, this is the image. This is the jellyfish image. And this image, as you can see, it looks very well detailed, and it has lots of features. However, as soon as you do a Fourier transform on this image, as soon as you do a Fourier transform on this image, you will notice that most of this image is filled with junk. So let me start. So first and foremost, I'm gonna run this part of the code. And once I run this code, what I see is I see the grayscale image. And I want to show you for a minute, I want you to look at uh, the A matrix and ABW. So this A matrix is the actual image, which is an RGB. That's why you have 1025, 1024 multiplied by 786. And there are three gradations of color RGB. So what you have is you have a tensor. So basically you have one matrix of R, second matrix of B, and third matrix of G. Now what we did, we read this image and then we represented this image as a grayscale image, and this is the grayscale representation of the image. So this is the grayscale image. And as soon as we converted that RGB image into a grayscale image, please notice that this tensor, which is like a brick of data, got converted into a plane of data, which means it only has X and Y. So it is just a matrix. Now what we are going to do is we are going to actually perform the FFT, the fast Fourier transform on this image. And I want to show you a very important aspect here, that this fast Fourier transform is not a fast Fourier transform on a time series. This fast Fourier transform is fast Fourier transform on the matrix. That's why we will have to use this FFT2, not just FFT, but FFT2 function that will create the fast Fourier transform on this entire image. So that's why we are using this FFT2. So highlight this and run. And once we do that, I want you to observe what happens. I want you to observe. Immediately we get this image. This image is the fast Fourier transform. Now this black and white, the representation is basically the intensity of the magnitude of the Fourier coefficients. What I want you to note, it significant portion of this image is black. There is a very some white, which is located in the center. So if you look at this center part, you will see that you have this part that is located in the center that has some significant component. But if you look at everything on the side, it's all gray or it's all dark, which means the components around this area, they are not significant. So here is what I'm going to do. What I'm going to do is I'm going to basically uh, capture this small portion of the image. So what I'm going to do is I'm just going to zoom in onto this image. Again, you see there is a lot of black spots. I'm going to zoom in onto this image and I'm going to capture the most important part in this image. Just I'm going to truncate only 5% all the way. I'm going to truncate the 95% of this image data set. So what I would do is I'm going to basically truncate this image data, this Fourier coefficient, just to retain these significant modes or significant numbers. So here is the next part. I'm going to sort this and then I'm going to keep just the lowest or the most important 5% of the numbers. And then what I will do is I'm going to plot these numbers just to see what is the relative strength. And then as you can see, everything here is black. And what I have is I have this most important data that is stored here. Now what has happened here is we have actually removed 95% of the junk data that was just filling the image. So there was no important information that is conveyed by that 95% of the data. We got rid of it and we just retained the 5% of the data that is actually contain some meaningful information. So what I'm going to do is I'm going to use this just 5% and then I'm going to capture the or reconstruct the image. And when I reconstruct the image, please note this image maintains all the finer details of the original image, but this image is of very small size. So what has happened is because of the approach that I have used here, I was able to save uh, a lot of space. So let me run this whole thing again. So if you look at the color representation and if you look at the surface representation, basically that shows you the compressed image and the compressed image as a surface, you would notice that my most important features, the significant features, are captured within the 5% threshold of this data. And that is super important. So this is the conventional approach that we talked about, that I'm going to use uh, some type of Fourier basis. Then I'm going to start uh, performing fast Fourier transform or wavelet transform. And then what I would do is I would actually go back and use that information uh, to capture the data. But what I want to say here is the alternate approach is using something called as the compressed sensing. Now, how do we utilize compressed sensing? So the principle of compressed sensing is few compressed measurements. So few compressed or random measurements can represent the sparse representation. In transform basis. So conceptually, the idea is very simple. We perform this random sampling in such a way that we essentially capture all the important part in the data. However, to solve this compressed sensing problem is not easy. This problem was polynomial hard. So polynomial hard problem. And what does this mean is we cannot solve this problem very easily. So it will take significant amount of resources. Uh, so this is also called as NP. So non-polynomial hard problem. So and non-polynomial hard problem. So this is extremely difficult to perform on computers. But then what happened? Basically, Professor Tao and Professor Cadence, they collaborated. Both of them are mathematicians and statisticians, and they developed the mathematical theory or the mathematical basis that actually provides guaranteed bounds on compressed sensing. So let's look at how this compressed sensing approach actually works. So let's understand that we have these measurements y, and we have this matrix C, and we have this x. So this x is called as the state, y is called as the measurement, and this is called as the C is called as the measurement matrix. So the goal of the compressed sensing, the goal of the compressed sensing is we want to find out a sparsest possible vector, sparsest possible vector, so that y is C psi s, where this guy is given as theta and s. So what does that mean? It means that this C is basically the matrix that is full of Gaussian or Bernoulli distributed random numbers. So what I want you to think about is that you have constructed this matrix C that is comprising of completely random numbers. But these random numbers, they follow a certain distribution. And that certain distribution could be Gaussian or it could be Bernoulli's. Now, what we can do is we can actually look at this representation y is equal to C psi s, where C times psi is given as theta. And then we want to find S, wherein S has lots of zeros. So we find the sparsest solution for S. Now what that means is, and I need to explain this once again. Imagine that you have a sort of an experimental data set, and what you want to do is you want to find out some type of relationship between variable y, and you want to find out the relationship between variable x. And the most natural way that can be done is fitting a straight line. What that means is we will use least square, or we'll try to minimize the squared of the distances from this line. And this is called as L2 norm. So we are going to minimize the perpendicular distance between the calculated value and the actual value. The problem here is, as soon as you have some data sets that are out of bounds or they are outliers, then your least square solution is completely out of whack. So we are not going to look at uh, yeah, so basically in this particular problem, uh, our hope is that S is linearly independent, but S is not fully populated, which means uh, S has a lot of entries that are zeros. And I'll explain that in just a second. Just bear with me. So if you have some outliers, then my solution or my straight line that is a best possible fit is not correct, because it may be true in L2 norm, but it doesn't represent the data. So the best way to solve these type of problems is something called as L1 norm. So if you have y, if you have x, and now imagine that you have data that is all over the place. Now this is exactly what happens. If you have data that is all over the place, fitting a least square solution is not the best approach. So what you want to do is you want to fit something called as L1 norm solution. Now L1 norm is, again, what it will do is, L1 norm is it will conveniently ignore the data set which is out of the bounds, and it will try to find out a line that is very close to the points that are cluttered together. So if you look at the definition of L1 norm, so if I want to find the L1 norm of this, L1 norm is nothing but, it's very simple. Least square is like you are going to find out these distances. So if this distance is delta x1, delta y1, so you will have all these delta xs square, then you will sum, and then basically try to find out the square root. In the least square norm, what we are going to do is we are going to find the square roots, a square of the square root. But here we will do, what we will do is we will actually find out the absolute value of the error between the true value and the fit, and then we will find the summation from k is equal to 1 to n sk. So what that means is, if I want to find out the L1 norm solution, if I want to find out the L1 norm solution, here is what I'm going to do. I have these points. What I'm going to do is, I'm going to try to fit a line. I'm going to try to fit a line wherein this distance A, this distance B, this distance C, this distance D, this distance E. So what I would do is, I would find out absolute value of A plus absolute value of B plus absolute value of C plus absolute value of D plus absolute value of E, and programmatically I would do it for all the possible lines. So I would consider all possible lines, and then I will fit the line wherein this distance, the L1 norm, is basically, or also called as the taxi cab norm, is minimum. So, and some of you may say, why is this called a taxi cab norm? It's also called as Manhattan norm, taxi cab, or Manhattan. Because if you want to go from point A to point B, a taxi driver would typically follow this route. A taxi driver, when a taxi driver is trying to go from point A to point B, that person is not going to find the least square distance. What it's going to do is, it's going to find out the shortest distance between those 2 points, and that path will be followed. So that's why this norm is called as the taxi cab norm. And this is given as S hat arg min S S1. So this is what it is. And what that means, what that translates to is, if I want to explain the graphical representation of these two norms, so consider L2 norm is like we are looking at the circle. So for an example, if you look at the point, you have this distance, which is y1, you have this distance, which is x1. So you are looking at the distance of the form x1 square, y1 square. If you look at, this is L2 norm. If you look at L1 norm, L1 norm is trying to find out the values which are given over here. So L1 norm, the solution. So for an example, if you want to find out the best possible solution, L2 norm will give you, your solution is x1 and y1, and L1 norm will give you the solution 0 and y1. So L2 norm will give the solution x1, y1, and L2 norm is going to give you the solution 0 and y1. Now please try to understand what happened here. L1 norm gave me a sparse solution. What does that mean? L1 norm gave me a solution where one of the variables or one of the values was 0. But L2 norm will give me the values where both of them are non-zeros. So if I want to find out the sparsest possible solution, which means the solution that comprises of zeros, I need to find out something called as the L1 norm. And I want to just give you another example. Say again, let's look at the apples and oranges. So I have 5 apples plus 2 oranges is equal to $3. I have 10 apples plus maybe 5 oranges is equal to $5, and I have 3 apples plus 8 oranges is equal to $10. Please understand, if I want to find out the L2 norm solution, what can happen is I would have to get a value of apple and the value of orange. So if I want to find out the L2 norm solution, my apple would cost me some dollar amount and my oranges will cost me some dollar amount. And this dollar amount, if you want to represent that graphically, it's like you will have to plot these three lines. So basically this would be the line, this would be the line, this would be the line. And then what's going to happen is you are going to find out the center of this, where this center is at the center of the circle that is inscribed between these lines. So what that means is in, if you zoom in, you would notice that these three lines and the solution L2, L1, L2 norm that is going to give you is something like this. This value is the solution given by L2 norm or least square. Now, what would happen if I were to do an L1 norm? So if I were to do an L1 norm, same thing, I would have three lines. I would have, and this is very important. So I would have three lines, same three lines. And maybe same three lines. But L1 norm solution could be this, L1 norm solution could be this, L1 norm solution could be this. And it depends upon how you fit it. So for an example, if you want to find out the L1 norm solution, what's going to happen is L1 norm would give me this solution, and that is because L1 norm is trying to give you the fit where you have uh, a square that is transcribed inside these equations. So this is L2 norm and this is L1 norm solution. Now, in theory, it makes perfect sense. But the question is, how do we do this in actual practice? Now, to do this, we have to actually use something called as convex optimization techniques. So we will have to use something called as convex optimization technique to perform this L1 minimization. And mathematically, this convex optimization is defined as S hat is equal to argmin taxicab or L1 norm subject to y is equal to c psi s. So if you think about the constraint, this is the constraint, and this becomes uh, a constrained optimization problem. And the important part here is, and this is what I want you to remember, that L1 norm solution is sparse, which means contains lot of zeros. L2 norm solution or least square solution is compopulated. What it means is very few zeros. So we are going to look at the MATLAB implementation of how this is done. And one thing to note is you would need computational power to perform these optimization problems, which means even though the theory for this was known, to implement this in a practical situation was difficult because it needed a large computational power. But what started happening is as the computational power started becoming cheaper, we could solve these optimization problems that at one point were time consuming in a reasonable time. So that's what made all this possible. And to the point that you can now have MATLAB solutions, or you can have MATLAB solvers or Python solvers that can solve these class of problems very easily. Now, what I want to do is I want to actually uh, give you the the specific conditions under which this is possible. And this is something that we have to remember. Conditions under which this compressed sensing approach works. Because many a times compressed sensing may not work. So we need to understand when would it work and when would it not. So the important case here is the measurement matrix C must be incoherent with respect to sparsifying basis. And this goes back to the question that we shall ask, are we looking at a linearly independent vector? So what that means is rows of C are not correlated with the columns of psi. And what that means, let me say y is equal to C psi s. So please note rows of C are not correlated with columns of psi. So, and this is something similar to the concept of independence, because what you are trying to find out is you are trying to find out the unique dimensions hidden in the data, and you are interested in finding out what is the value along that particular dimension. But since we are working in the random variable theory, please understand it's not a deterministic variable. The variables that we are talking about is random. We consider the concept of coherence. We consider the concept of coherence that actually indicates that the terms are not correlated. What that means is change here has no relation to change here. So this is exactly similar to the concept of linear dependence or independence, because now what you have is you have these rows and columns that have no relation whatsoever with respect to each other, which means when you have used these as your basis vectors, they are going to capture some aspect of the data that will not be captured by the other basis. So that way you are capturing everything in that basis. So this is very important condition. And the second important condition is the number of measurements I'm going to call them P, must be sufficiently large and that when I say that large means P, the order of the P, this O is an order symbol, which is order of K log N by K. So what that means is this is actually a huge number. So this can also be represented as K1 K log N divided by K. And this constant K is dependent on the level of incoherence. Now, what does that mean? If you were to look at purely from the linear algebra angle, if you look at this particular problem purely from the linear algebra problem, one thing that stands out is this matrix, which is C times psi. This matrix is a unitary matrix, or it's a unitary transformation. Now, once a side note, and I just want to talk about this, is imagine if you have a signal, that is varying, something like this. If you have this signal that is varying, and this signal has multiple frequencies. So this signal has say 10 hertz signal, 20 hertz signal, 50 hertz signal, which means there is a component that is changing 10 cycles per second. There is another component that is changing 20 cycles per second, and there is another component that is changing 50 cycles per second. And all these components are on top of each other. So this signal comprises of maybe three terms, wherein one signal is changing at 10 cycles, other signal is changing at 20 cycles, the third signal is changing at 50 cycles. Now, if we want to capture this signal, which means if I want to digitize this signal for digitization, or to capture the signal, I need to sample this signal at least at 100 hertz, which means I need to be taking the snapshots at 100 times per second, 100 times per second. Only then I'm able to capture these ups and downs or peaks and the valleys of this signal. Now, when we are thinking about the compressed sensing, this problem is formulated in a slightly different fashion. And this is something called as the Nyquist criteria, or also called as Shannon's sampling theorem. Which means if you want to sample this signal, you need to be taking snapshots that are twice the frequency of the fastest signal. The fastest signal, the signal that is changing very quickly, is 50 hertz. If you want to capture this data, or if you want to convert this signal into some type of a digital representation, you need to sample it at 100 hertz. Now, what is happening in the compressed sensing? Now, I want you to quickly look at this term. So I want you to look at this term. Please understand, C times psi is nothing but a matrix with random entries. C times psi is nothing but it's a matrix with random entries. And now if I'm gonna do the compressed sensing, what's gonna happen is, please try to understand, here my sampling is going to be like this. Now what that means is the time period between each sample will be different. So here, please understand, the time period, which is time between snapshots, is constant. But now when I'm going to look at the compressed sensing, what I'm looking at is I have this matrix C times psi, C times psi. This is the incoherent, or basically the random matrix with maximum incoherence. So it is incoherent. So what that means is the time period, this is extremely important. time period, which is time between samples or time between snapshots, changes, not constant. So varies. Now, here, what this varies mean is essentially is this variation is captured in the non-correlation between the rows and columns. Now, what does that mean? That means once you perform the compressed sensing, imagine if you have a signal, that signal is something like this. If you try to perform compressed sensing, and I'm trying to give you a sort of uh, example, which is more intuitive, uh, but it's strictly not mathematically not compressed sensing. But I want to tell you what is happening. So you have a signal and you want to capture it. If you use the Nyquist criteria, this signal has a frequency of say 10 hertz. So by Nyquist criteria, you need to sample at 20 hertz. So by Nyquist criteria, you are going to sample, 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 sample. So you are going to perform these many samples to capture this dip. And this sampling is needed because this small part of the signal is higher frequency. Now, in contrast, if you are going to do the compressed sensing, what will happen is the compressed sensing will actually sense this, something like this. And here, so this is exactly what is happening in compressed sensing. When you are trying to do the Nyquist sampling or the usual sampling, this delta t is going to be constant. But when you are doing compressed sensing, because of this product, which is C times psi, which is incoherent, what that translates to is you are going to have this as delta T1, this as delta T2, and as soon as you are trying to capture some important features of the data, automatically and mathematically, basically this sampling will be reduced. So delta T3. And as soon as the data feature remains constant, again the time sampling would increase. So loosely speaking, this is what is happening in compressed sensing. And again, so what we are going to do is we are going to look at some very particular examples of compressed sensing. We will look at the compressed sensing application to something called as the signal reconstruction. So what I have shown you here uh, will make perfect sense when we are going to do the MATLAB coding, and then we are going to perform this compressed sensing on an actual data set, wherein we would use the Nyquist based sampling, and then we'll use the compressed sensing. And you will notice that the data that we capture is fairly accurate. So we get the complete uh, capture. Now, one thing that I want to tell you is the compressed sensing is based on something called as the quality of the measurement, which means if your measurements are bad, then the compressed sensing is not going to work. So mathematically, there are algorithms and there are checks that actually make sure that your measurement is working. And L1 norm that we talked about, the taxi cab and the uh, Manhattan norm, is actually before compressed sensing. And this is discussed a lot in case something called as parsimonious statistical modeling. Parsimonious statistical models. So parsimonious means sort of frugal. So parsimonious means frugal, which means do not use overly complicated models for statistical analysis. For an example, if you want to fit a regression, do not use L2 norm, just use the best possible solution that that works okay with most of the data. So we don't want it to work perfectly with all the data. We want to work it the best possible uh, way for the most of the data. So as we discussed earlier, that parsimonious statistical model uses something called as the L1 norm, and there is something called as the technique, which is called as the lasso, which is add something called as a penalty term, and that penalty term allows you to find out the parsimonious model or the frugal model. And we will talk about, and this has a lot of significance in signal processing, statistical machine learning, and data analysis. So we will talk about what is lasso, how is lasso applied, and then we will actually look at a few MATLAB examples of compressed sensing for signal capture, signal reconstruction, and image capture. Okay, with that, I'm gonna stop here, but I would be happy to answer any questions you may have.